Okay. Our next talk is talk of Andrei Malyutin, node transformation and conditions of link non-splittability. Please start.
Thanks very much, and thanks to our organizers. Very pleasant conference. And my talk is about node transformations and conditions of link non-splittability. The story is that we with colleagues study the structure of the set of node and its statistics, and this topic has a lot of relations with almost all node theory, I think maybe with all node theory, and we extensively use node transformations. Node transformations, that if you have a spatial link, you just usually transform some local part of it. And in some places, we need to know whether some link is non-splittable, because if you have a spatial node and there you want to tie an additional local small node over the old one, you do it via transformators. You have a little circle in the complement of your node, and to be sure that the result of your transformation is non-trivial, you should find how this small local node, trivial node, linked to your node, or it's free and splittable. So, and today we'll show you a new lemma about conditions of splittability. The name of this one is Tomsk lemma because it was invented in April 2023 during the conference devoted to 60th anniversary of Andrei Malyutin. So it's Tomsk lemma, and with condition of unsplittability of two-component link, and to understand it, you need the definition of unknotted torus with a hole. So unknotted torus with a hole in a three space in a three-dimensional sphere is just you take an unknotted torus and make a hole in it. So these 3 and 4 examples of hole toruses, you can see it can look quite different. So the first one is disk with 2 holes and tube added there is the example of a knotted torus. We need much more than others. And to see the sense of it, of course, you should understand that the shape of this knotted torus can be like the second, third, or fourth picture. The second picture is just this torus with a hole. The second one, when the hole is stretched, and the last one is when the hole is stretched a lot. So the last one is also just a torus with a hole. So, and this Tomsk lemma sounds like follows. If we have a node in a 3-dimensional sphere, or let it be in 3 space, and let W be some unknotted torus with a hole like that in the complement of your node. And then suppose you choose some meridian and longitude pair on your whole torus. For the torus, when we have unknotted torus, we have a meridian and longitude as isotopic classes of some simple curves on your torus. When you are in a 3-dimensional space, you have a meridian and a longitude, and when you in a 3-dimensional sphere and you have such unknotted torus, then you have exchange what is meridian and which one is longitude. It's the same, so you can exchange it. So I just call it meridian longitude pair. But if we are in S3 for an annotated torus, its exchange is the same. Moreover, when we are in R3 in a three-dimensional space, and we have a torus and not a torus with the hole, again, there is no difference between meridians and longitude because of this hole. So yeah, I can't define which one is meridian and which one is longitude. But suppose we have this pair, yeah, and you can see it on the left, in the left picture, with red one is, say, longitude or meridian, okay. And another colored one is meridian. So, and if we have a knot and the unknotted torus with the hole in the knot's complement, and there we choose some meridian longitude pair, and we see that this meridian and longitude didn't linked with our knot. Formally means that the two component link obtained by our knot and our meridian is non-splittable. So we can't find some sphere that splits this, our two-dimensional sphere that splits our space or three-dimensional sphere in two parts, such that one part contains one component and another part contains the second one. So it's unsplittable, it's linked, non-splittable, yeah? So suppose that our meridian that lies on our torus with a hole is linked with our knot, and suppose that our longitude on this line, on this torus with a hole, also linked with our knot. Then this means that the boundary of our hole in the torus will also be linked with our knot. So the two component link obtained by our knot and this boundary is non-splittable. Hmm? Yes, yes, of course. Yeah, it's obvious. I can 30 seconds. If you have, say, okay, I think you could see it on the following pictures there. But first, I should say that in addition to this question, you can see that in fact, yesterday when preparing these slides, I realized that in fact, these conditions of linking of these two classes and linking of the boundary of the whole are equivalent. So in fact, we can upgrade it. So again, we have a knot, we have a hold torus in the complement of this knot, and then these two conditions, that a meridian and a longitude of this whole torus are linked with our knot, is equivalent to the conditions that the boundary of our hole is linked with our knot. In fact, you see, when do these transformations, usually we try to, if we have some knot and want to do transformations of this kind, we need this small unknotted circle in knot complement and checking just how to link this circle with our knot. Usually, the linking number criterion works. So, and this one is a special lemma what to do when in your situation you need do some transformations when the simplest linking number criterion do not work. So this special case, this lemma is not something abstract. This really needed for work in the situation when you can't find the simplest case when your additional circle just linked with your node via the linking number criteria. And here's some remarks, some comments on this. First, the interesting moment is that, say, for the linking number, when you're just checking whether something linked to your node, in algebraic way, it doesn't matter whether you have a node or link. And with this lemma, at the moment we have only geometric proof, and it turns out that it's very important that this thing is really a node. If you replace in this formulation our node with a link, the lemma will fail, because just, you see, so it, for example, our lemma states that if this is a part of our node and this is our additional circle, which is the boundary of our whole torus, you can see it like this one goes here. So our lemma states that in this case, if this red guy is a part of our node, then this black guy will be linked with him. And of course, it's not true with links, because we just have this link and then this unlinked with it. Another remark is just that, of course, when you have a proof, you can see how to generalize it to the case of surfaces of larger genus. But in fact, I formulate now just for the whole torus and not the whole surface of any genera, because when I try to generalize, it turns out that in the case with the torus, I need only two curves, longitude and meridian one. And in general case, if I generalize straightforward, it turns out that to upgrade lemma, I need an infinite family of curves, just isotopic classes of boundaries of all compressing disks. And we have a lot of such disks, but I hope that should be some way to transform this formulation to a finite number. But at the moment, I don't know, and this is the new question. Maybe somehow you can help in this question to solve it, how to reduce it to finite number. If I had time, at the end of my talk, I will briefly sketch the proof, and you will see how to, maybe somebody will see how to do it for general case, maybe, because it's just this kind of lemmas is just based on geometric tricks. And it's usual way that people who study some direction a long time just can't see some simple geometric trick, and somebody who see the first time just see this trick. So there is a hope that somebody of you, if you listen to the end, will just help to solve it. It's usual thing with this such an objects, just to see some geometric way to restrict it. And another remark about this algebraic and geometric methods, I believe that perhaps there is some algebraic way to prove this lemma. This remark about the node and links shows that maybe it's not completely something trivial, because it makes difference with nodes and links, but maybe some algebraic way to prove all this will work in this case, notwithstanding that this difference between nodes and links. Yes, and then that why we need this lemma. So this lemma is just provide us with local conditions of two-component links non-splittability. So we can apply it to concrete nodes, yeah, to transform it. And we have, in fact, we have infinite series of concrete particular conditions of non-splittability from this general lemma. Yeah, as an example, let me go here. If we have from the left, you see we have a local part of our node like this. Yeah, see this one going from above to down. This our node. And this guy in the center is our torus with a hole, yeah? And the boundary of our hole is just this boundary of this horizontal disk with two holes, which is a part of our torus with a hole, yeah? So our lemma shows, in fact, that this circle, this is the boundary of this horizontal disk, is linked with our node, and this provides a local condition of non-trivial linkage. Yeah, so we can draw a concrete shape, concrete local shape of our node, and to state that this concrete circle is linked with our node, even if we know only this local part of our node. And so we can get an infinite number of local shapes of local node parts that guarantee that this linkage. So we have some infinite family, and usually in a complex node, to see that something is linked, you check several parts of node to show this. First, these two circles are linked, and then these two circles provide a meridian and a longitude for this whole torus. Then we go to the boundary of this whole torus. Then we see that we have another linked circle, and this circle, which is a boundary of the that whole torus, with this additional second circle, will be the per meridian and longitude for another whole torus, which boundary you now know that linked, and so on and so on. So this repetition leads you to a series of some series of linked circles. And here's an example. This is a picture provided by Alexei Miller in his work, and in his talk he showed it. This is a part of a node. So we had some node, and then we transform it, adding new these tangles. And this is a picture from his proof, from Alexei's proof, that we can obtain a special part in the Gordian complex of any node. So initially, we had some node out of this square, and then we make some construction, adding additional structures for our node, transforming it, adding some new arcs in this square. And then this is at some point of our iterative process, we see such a configuration. And for this one, we can guarantee that the notings in that small balls marked P2, P1, 2, P2, 1, 2, 2, we can prove that the local nodes in these small circles and the uncompressed in the toruses above these local notings are incompressible because we, from our lemma, from Tom's lemma, we know that a circle over each pair of strings of this construction going through any z P2 or P1, this circle going over these two strings is linked with our node by this Tom's lemma. And to show it, we apply our lemma iteratively. So first, we see that, say, in this part, we see that a circle that goes over these two strings is linked with our node because of this construction on the right. Then we go further and see that a circle that goes over these four strands also linked with our node, and so on. We can check that a circle here, then a circle here, and so on, higher and higher. All these circles are linked with our node via iterative application of our lemma. And this gives this theorem as corollary. Of course, the main point of this theorem, this is the construction itself that Alexei made with Ilya. And our lemma is just some tool to show that this construction, this very intricate, very complex construction really works. So in fact, the main part of the work is, of course, the construction itself. And this lemma is additional tool to show that it really works. And this is the theorem, and this is the theorem with a corollary for Gordian complexes. And as Andrei Yuryevich said, now we formulate it in terms of complexes, and instead of infinite complete subgraphs, we have this infinitely high dimensional simplices. So I hope that it's okay now. So the theorem said that if you have two in the Gordian complex is just the complex where the vertices are the isotopic classes of all nodes, and two nodes make an edge if they are related by the crossing change, and a k-tuple of nodes in our complex is the vertices of a simplex if each pair of this k-tuple can be made one from another by a crossing change. So, and this picture shows that how to construct this set of vertices that makes an infinite dimensional simplex for a given pair of vertices of nodes that are on distance 2 in our Gordian complex. So you see the initial pair of nodes are out of this picture, and these two crossings are two crossings that makes the distance between these two nodes. So initially you can imagine on this picture just two small arcs on the bottom, and one arc going, one large unknotted arc going through these two ones. Whenever you have two knots in the Gordian complex at distance 2, you can find a diagram for these two knots when the difference in these diagrams only in this square, and the difference is the first knot has only two small arcs there on the bottom and nothing else. And the second knot has these two small arcs and one arc going through these two first ones. Yeah. So one knot distinguished from other only in two crossings. So you have such picture. And then for this pair of knots, Alexei constructed a series of knots over this, complexifying this initial picture with three arcs. More and more and more new transformations. And this series gives us this simplex. And now it is known that in this Gordian complex, each edge is contained in an infinite dimensional simplex. So a corollary is that for any two vertices of Gordian complex, their links, it's a bad terminology, links not in the terms of link theory, links in terms that it's spheres around the vertices. One spheres in terms of simplicial complexes, you can imagine a link, the link of a vertex, just like a sphere of radius 1 in your complex. So, and usual terminology is link for this. Right. So in the Gordian complex, for any two vertices, these links, these spheres of radius 1 around these vertices will have either empty intersection, or their intersection contains an infinite dimensional simplex. Why? Because if the vertices coincide, we know that the sphere, this link of vertex is large. If they are at distance 1, they are connected by an edge. And we know from old works that two vertices connected by an edge, if we have two vertices connected by an edge in a Gordian complex, then this edge, in fact, is a part of an infinite dimensional simplex. Then this theorem covers the situation with distance 2. If we have two vertices at distance 2, then from this theorem, we see that these links intersects over some infinite dimensional simplex. And then if we have distance 3 or larger, then the intersection is empty. So now we see that objects are huge there. In fact, I think that instead of vertices, we can say that for any two subsets of the Gordian complex, their stars, either intersections, the intersection of the stars of these two subsets, either empty or contains an infinitely high dimensional simplex. And if I had some more time, I will maybe say something about the proof. Yeah. So it's a short scheme. It was too late yesterday to think about it. So maybe it's a very nice idea. So again, our lemma, Tom's lemma in this extended form with two equivalent conditions. And now we have, we want to check the proof that if our knot, we have a knot, we have a torus with a hole, and suppose we know that a meridian and the longitude of our torus with a hole are linked with our knot. We want to prove that then the whole of our torus is also linked. Yeah, and our method is purely geometrical. If you see about the geometrical and algebraic methods in knot theory, this is geometrical method, and I want some algebraic from you maybe. If but in fact, maybe to try algebraic, maybe it's better not to listen to this geometric proof. I don't know. If somebody don't want to listen to geometric and want to think about algebraic first, please go out. So we know that M and L are linked with K, and want to show that the boundary of our hole is also linked. Suppose, on the contrary, that this boundary of our whole torus, this dw, is not linked with our knot. This just if this k with dw is splittable. Suppose, on the contrary, you want to come to some controversial statement, and we assume that it can be unlinked. Then, if it can be unlinked, we have some, say, smooth disk in knot complement whose boundary is our circle boundary of the boundary of our hole. Yeah. Then we can, by standard techniques, we can isotope D into irregular position this disk with respect to our torus with a hole. So we have two surfaces with the same boundary. We are given this torus with a hole, and the boundary of this hole is our circle. And we have some disk whose boundary is this circle. This disk can generally intersect our torus with a hole, but we can send it to a regular position when this intersection is just a family of circles. Yeah. And in this family of circles, we can take some that is the innermost on our disk. And then we see another disk B in our disk D, such that this B is glued somewhere to our whole torus, and it intersects, this B intersects, not like D, this B intersects our torus only in its boundary. Yeah? So initially we have a whole torus and some disks with the same boundary that maybe intersect this whole torus in some other places. And now we obtained in this large disk D some small disk B that intersects our whole torus only in its by boundary. So it's glued to our thing. And then we have just consider 4 cases if we have unknoted and hole with a torus with a hole in a 3 space, and some disk is glued such that the interior of this disk doesn't intersect this torus, and only the boundary of the disk lies on the torus with a hole. Then we have only 4 possibilities. So this boundary is isotopic to a meridian. Maybe this boundary is isotopic to a parallel. Maybe it is contractible, or maybe it is isotopic to the hole itself. And in each case, we see that this is impossible, because if our boundary of this, our small disk, is exactly the isotopic class of the meridian, we will see that then condition of meridian linkage with our node will fail. So it's impossible. The same with the longitude. Then a little bit more complex with contractibility. So if we have a contractible circle, so if our small disk glued to our torus, his boundary is contractible, then we have two more cases. Either B is reducible, so this B glued on the torus together with some disk on the torus bound a ball. Then we have the rest of the torus and the knot either inside this ball, either outside. If the knot is outside this ball, yeah, then we can shrink this B and obtain new disk, some new disk D prime, say, which has a smaller intersection. We just reduce and use this reduction. And if our knot is inside this ball, so ball is have a torus and disk glued to it, and some ball here. If the knot inside this ball, then it can't be linked with either meridian or longitude, or both, in fact. So this is impossible also, and so on. If the last case is that if the boundary of this our disk is isotopic to our hole, then we just obtain a torus, just slightly modified initial torus with a hole. We just glue with this hole, almost glue it with this new disk, and obtain a torus which is in the complement of our initial knot, and that contains our whole torus. This is impossible because this new torus should have the same meridian and longitude as initial whole torus. And if you have a knot and some torus in its complement, then at least one of meridian and longitude can't be linked with your knot, because all your knot lies, if you have a torus in not a torus in linked complement, in knot complement, then the knot entirely lies either in the solid torus, in one of the solid tori bounded by this unknotted torus. And almost the same, so we checked all possibilities, and in one possibility we have a reduction, and all other possibilities are impossible. And only thing we use is just surfaces, yeah? And so it's purely geometric, and the proof vice versa is completely similar. Again, now we suppose that we have that again knot torus with a hole, and now suppose the boundary of this torus with the hole is linked with our knot. Then we can show that one of these guys should be linked. Again, supposed on the contrary that neither of meridian and the longitude is linked, then there is a disk that in the complement of our knot with the boundary this unlinked longitude or meridian, choose any. And then we just similarly analyze the position of this disk, again found that some subdisk, and similarly just goes through subcases. I see that nobody really follows, so I think it's enough to study. Yeah. to study this scheme of proof. I think that it was several lines, and I think that it's a short scheme, but now I see that it's not so short. Okay, but the sense is it's a purely geometric thing, and I hope that some algebraic, we see that linking number doesn't work here, but we hope that some algebraic idea, maybe with polynomials or something like that, can have the similar shape and will prove something in more general settings. Okay. So thanks. I think that's all.
Thank you very much. Are there any questions, comments? Is it possible to generalize the Tomsk lemma to noted tori by adding some more conditions?
I think, yes, it's easy to check. You should just take these schemes, proof schemes, and instead of unnoted torus, take a noted one, and just go step by step, and you will see where you
Yes, and
will
in the
need
last
to transform something, or you will see that it doesn't work at all. Yeah, but I didn't check yet. But you can do.
Okay, thank you.
Thanks for the question.
Are there any other questions? So maybe the point you use you have not, but not a link is the last of the four cases. In the last case,
Yeah.
you use that.
Yeah, and
is
in
enough.
this geometric set, we can't upgrade. So if we have link, so we don't know what to do if it is linked. There is no way to modify this construction.
Okay. So if there is no other questions, let us thank the speaker again.
Thanks.